Hi everyone. A warm welcome to all who are watching my PPT. This is M. Pavan from Data Science Group D section. I am here to discuss one topic called the orthogonal projection matrices on the eigenspaces of the DFT-IV matrix. We will learn more about this topic and we will get more knowledge and confidence in this topic. We will move on to next slides to learn more about this topic. Okay, we'll going to next slide. Introduction. The discrete Fourier transmit DFT not only enables fast implementation of the discrete convolution operation implementation, which is critical for the efficient processing of analog signals through digital means, but it also represents a rich and beautiful analytical structure that is intersecting on its own. Means the DFT not only enables fast implementation of the discrete convolution operation, which is critical for the efficient processing of the diagonal signals through digital means, but it also represents a rich and beautiful analytical structure that is inter, inter interacting on its own. A typical senior level digital signal processing DSP course involves a fairly detailed treatment of DFT. Means apart from DFT, we have another called a typical senior level digital signal processing DSP course involves a fairly detailed treatment of DFT and a list of related topics such as circular shift, coloration, convolution operations, and the connection of circular operations with the linear operations. Means in this DSP we have many topics and they're listed as circular shift, coloration, convolution operations, and the correct connection of circular operations with the linear operations. Next, we move on to next slide. Next, our goals our goals are to study the eigenvalues and eigenvectors of the DFT matrix to determine the multiplicity of the eigenvalues, to define the invariant subspaces under the DFT mapping, to construct the projectors to the invariant subspaces, and to underline some connections between intervenient subspaces and other transforms. Means in our topic, our goals is to learn about eigenvalues and eigenvectors of the DFT matrix, to determine the multiplicity of the eigenvalues, to define the invariant subspaces under DFT mapping, to construct the projectors to the invariant subspaces, and to underline some connections between invariant subspaces and other transforms. The eigenvalues of a matrix are by definition the roots of its characteristic polynomial. The eigenvalues of the matrix are by definition the roots of its characteristic polynomial. Next, we move on to next slide to learn more. Here we're having eigenvalues, eigenspaces, and projectors to eigenspaces. The eigenvalues of a matrix are, by definition, the roots of its characteristic polynomial. Here we do not calculate the characteristic polynomial explicitly, but relate the powers of f to the characteristic polynomial. Means the eigenvalues of a matrix are defined the roots of its characteristic polynomial. Here we do not calculate the characteristic polynomial explicitly, but we relate the powers of f to the characteristic polynomial. Let J denote the second power of the matrix F, that is J5FT. The matrices of matrix J can be calculated. Means the J denotes the second power of the matrix F, that is JFFT. The matrices, the entries of matrix J can be calculated. Next, we move on to next slide to learn. The notation of 1 as 2n indicates the module n reduction of 1 2, that is 1n1k 2n as 1n1k2 module n. It can be seen that the J matrix is a permutation matrix that maps 3n4s 3n12n 2n4. The J matrix is called a coordinate intervention or reflection matrix in the lecture. Means the notation which indicates the module n reduction of that is, it can be seen that the J matrix is a permutation matrix that maps from here to there. The J matrix is called a coordinate intervention or reflection matrix in the literature. Two coordinate inversion operations executed in a row can be denoted by J2 or F4, since two coordinate inversions result in the identify mapping F4 is equal to I. Means two coordinate inversion operations executed in a row can be denoted by J2 or F4. Since two coordinate inversions result in the identity mapping, F4 is equal to I. Next, we move on to next slide. The multiplicity of eigenvalues. The eigenvalue multiplicity problem of DFT matrix is known to be a difficult problem. We present a solution to the eigenvalue multiplicity problem using an equally difficult result known as the Gaussian sum. Means the eigenvalue multiplicity problems which we do in DFT matrices are known to be difficult problems and are well known to everyone that we present a solution to the eigenvalue multiplicity problems using a equally difficult result. Means as the question was a difficult problem, we will give solution also in a difficult result known as the Gaussian sum. In 1972, J. McCullen solved the eigenvalue multiplicity problem using elementary. Means McConnell's solution can be considered as another proof of the Gaussian sum and residues at the intersection of pure and applied mathematics as noted. Means in earlier 20s, exact 1972, J. McClellan, who is the one first solved the eigenvalue multiplicity problem which we are discussing. That problem was first solved by J. McClellan's in 1972 using elementary means bracket 4. McClellan's solution can be considered as the another proof of the Gaussian sum. Means as we said before, multiplicity problem you are solved the solution using a equally difficult result known as the Gaussian sum. This McClellan's solution is considered as another proof for that Gaussian sum and resides at the intersection of pure and applied mathematics as noted. This can be considered as another proof for the McClellan's solution. This Gaussian sum and McClellan's solutions are the two proofs for our problem in DFT matrices. The problems are eigenvalue multiplicity problems of DFT matrices. Here we are getting two proofs for that. Next, move on further slide. Maclaurin is also known for a optimal filter design technique, Park's Maclaurin algorithm, and a multi-dimensional filter design technique through mapping. Maclaurin transform to the DSP community. As I said before about DSP, now Mr. Maclaurin is also well known for optical filter design technique, Park's Maclaurin algorithm, and a multi-dimensional filter design technique through mapping. These both are included in DSP community. As I said before about DSP, the DSP in the DSP community, these both are involving. It can be noted that the trace of the matrix Pk is equal to the multiplicity of the eigenvalue with value Ik. This can be justified from equation 1 by using the identity trace AB is equal to trace BA. Means it can be noted, means we should be remember that trace of the matrix is equal to the multiplicity of the eigenvalues of the of the value eigenvalue with value. This can be justified from equation 1. By using the identity, we can easily tell that trace of AB is equal to trace of BA. Means both the traces, whatever we are doing, A into B or B into A, both the traces will be similar and equal to each other, as trace of AB is equal to trace of BA. Then we will move on to next slide. Eigenvectors of DFT matrix. Means till now we just discussed about eigenvalues and eigenvalue problems in DFT vectors. Means from till now we just discussed only eigenvalues only. Then now we are discussing about eigenvectors, which are the second step or the next step of the eigenvalues. After we are finding eigenvalues, we need to find the eigenvectors. Then we can have a matrix of eigenvectors, son of DFT matrix. So as we now till now we learned about how to prepare, how to do prepare a eigenvalues. With that eigenvalues only, we need to prepare eigenvectors. Now we will learn more about how to prepare eigenvectors and with eigenvalues. The eigenvector set of DFT matrices for n greater than or equal to 4 are not unique due to the eigenvalue. Due to the eigenvalue multiplicity problem as shown in table 1. The table indicates that there are indefinitely many eigenvectors set of DFT matrix. Means as I said now, eigenvectors are coming from eigenvalues and the eigenvalues multiplicity problems. The table indicates that there are infinitely many eigenvectors sets of DFT matrix. We have examined the structure of DFT eigenspaces and used the projectors to the invariant spaces to establish more connections with the relatives of the Fourier transform. Means here we are having a term called eigenspaces. What is eigenspaces? Eigenspaces and eigenvalues both are same. Those are not different. Both eigenvalues or eigenvectors gives the same meaning. So here we are using eigenspaces. Here what he was telling is we are examined the structure of DFT eigenspaces and used the projectors to the invariant spaces to establish some connections to the relatives of the Fourier transform. Then we will move on to next slides. Extensions means we can extend the problem up to we getting a suitable solution. Then we are doing the extensions from here. Put to this point, we have presented results on a one-dimensional conventional DFT matrix. In this session, we extend the earlier results to non-conventional DFT matrices and multi-dimensional DFT matrices and establish some connections with other relatives of the Fourier transform. Up to the point, we have presented results on a one-dimensional conventional DFT matrix. In this session, we extend the earlier results to non-conventional DFT matrices and multi-dimensional DFT matrices and establish some connections with other relatives of the Fourier transform. Means we are extending the results to the non-conventional DFT matrices and multi-dimensional DFT matrices, and we establish some connections with other relatives of the Fourier transform. Next, we will move on to next slide. Now, as we done with extensions, next eigenstructure of off-shift DFT. The off-shift DFT has two parameters A and B that can be freely selected. It can be shown that the offset DFT matrix is unitary and reduces to the conventional DFT when AB B5O. The eigenstructure of the offset DFT has been shown to be closely related to ordinary DFT for the special case. The other cases are a little more complicated and studied under the categories of integers and A1 B5 integer and A1 B2 integer. Means eigenstructures of offset DFT. Means eigenstructures or eigenvectors are same. The offset DFT has two parameters A and B that can be freely selected. It can be shown that the offset DFT matrix is unitary and reduces to the conventional DFT when A and B fit. And next we move on to next slide. Eigenstructure of multidimensional DFT. Means we are going to learn about differences in eigenstructures in unidimensional and multidimensional and so on. By definition, the multidimensional DFT is a separable transmission. Hence, a two-dimensional DFT operation can be interpreted as the cascade application of a one-dimensional DFT to the column of the input, a matrix, following by the application of DFT to the rows of the resultant matrix. Means multidimensional DFT is a separable transformation. Hence, a two-dimensional DFT operation can be interpreted as the cascade application of the one-dimensional DFT. Means the result of a two-dimensional DFT can be easily extended to multi-dimensions. Next, we will move on to next slide. Relations to other transforms. Means we have so many relations in that we are discussing some. The projectors to the invariant spaces of the DFT can be used to characterize other relatives of the Fourier transform. It can be noted that at the projector define an algebra for the relatives of the Fourier transform. More information on the fractional Fourier transform and the details of the definition multiplicity problem can be found. Next, we will move on. Here we came for conclusion. We have examined the structure of DFT region spaces and used the projectors to the invariant spaces to establish some connections with the relatives of the Fourier transform. The presented results are heavily based on the projector properties of projectors that can also be of interest on their own due to their strong algebraic structure and important geometric interpretations. And thank you for giving me this opportunity to explain you about this topic. And I hope all understand my topic. Thank you all.